Hi, I'm Sehaj Dhingra. I'm a 16-year-old high school student from Delhi, India, and I am here to present you my literature review on the aerodynamics of micro-air vehicles at low Reynolds numbers. I carried out my research under my mentor, Miss Joy Watson, and she is a mathematics PhD student at George Watson University. We'll be going in a flow wherein I will first introduce my research. We'll go over the low Reynolds number. We'll go over the modeling of the research and the designs of MAVs, numerical solutions to them, bio-inspired approaches, and finally the conclusion. To begin, micro-air vehicles or MAVs are very small aircrafts, usually weigh less than 200 grams and with wingspans shorter than 15 centimeters. To give you a sense, that's about the size of your hand. Because of their small size, they operate in a very different aerodynamic environment compared to conventional airplanes. This is described using a concept called the Reynolds number. The Reynolds number is a dimensionless value that compares how strong inertia, which is the tendency of air to keep moving, is to how strong the viscosity, which is the stickiness of air, is. In big airplanes, Reynolds numbers are in the millions, meaning the flow is mostly turbulent and predictable. But for micro air vehicles, Reynolds numbers are in tens of thousands, which means air acts stickier and flows separate easier and change effects dominate. And basically, think of it this way. If you're swimming in normal water versus a bee swimming through honey, that is how air works for microwave vehicles in comparison to normal aircrafts. They say it makes it much harder for MAVs to generate enough lift, which is the upward force that keeps an aircraft in the air, while drag, which is the resisting force pulling it back, is proportionally higher. All of this makes micro air vehicle design and control more challenging. That is exactly why researchers are exploring specialized approaches in aerodynamics, mathematical modeling, optimization, and even bio inspired designs that borrow ideas from birds and insects. Right. So moving on to the low runners number aerodynamics. One of the most unusual aspects of micro air vehicle flight is their behavior at low runners numbers. Low runners numbers aerodynamics means that air behaves differently than it does for big planes. At these scales, smooth airflow called laminar flow separates easily from the wing surface, creating something called laminar separation bubble. This bubble, it reduces lift and it increases drag, making the flight less efficient. Experiments by Pelissier and Mueller in 2000 tested very thin, flat, and cambered planes. Camber here means that the curvature of a wing. They found that curved wings or cambered plates perform much better than flat plates at Reynolds numbers between 60,000 and 200,000. Mueller and Delorier later emphasized how these separation bubbles dominate MAV aerodynamics. In other words, the kind of airfoils used for commercial aircrafts simply do not work at MAV scale. The big takeaway here is that small wings need custom, low runner number designs. Normal airplane wings aren't suitable because MAVs live in an environment where viscosity and separation effects rule. Moving on to modeling and optimization. Beyond basic aerodynamics, MAVs also need strong mathematical models to predict their behavior and keep them stable. A 6-degree freedom of model developed by Candith and colleagues in 2018, including propeller wake effects, which you can see on the left side of the screen. The propeller wake is the swirling flow of air created by the propeller. For MAVs, the wings are so close to the propeller that this airflow directly changes the wing's flight and drag. They found that lightweight MAVs are very sensitive to disturbances like wind gusts, which are sudden short bursts of winds, and because MAVs are so light, even a small gust can knock them off course. But by using feedback controllers, Automatic systems that constantly sense the MAV's position and correct its movement, stability can be maintained. On the design side, optimization has been widely applied to MAVs. Sharma and Narasimha, for example, optimized wing twist and shape, which improved endurance by nearly 40%. Nepal designed rotor airfoils specifically for low Reynolds numbers, reducing drag and delaying stall. And Yong and Dole showed that new propeller shapes could produce more thrust, but at the cost of higher drag. The lesson here is that optimization improves performance, but it always involves trade offs. You cannot specifically maximize everything at once. If you want more lift, you may have to sacrifice on efficiency, and vice versa. Moving on, we will look at numerical simulations and bio inspired approaches. Computer simulations or numerical simulations are powerful because they let us study airflow patterns that are difficult to capture in experiments. For example, in 2005, researchers simulated the Colorado MAB, which had a flexible membrane wing. They found that it could reach unusually high stall angles, around 30 degrees, because of strong tip vortices. A tip vortex is a swirling air current at the edge of the wing. It can sometimes add lift, but it also increases drag. Despite the high stall angle, the MAV's lift to drag ratio was still low, showing the limits of its efficiency. On the other hand, nature gives us powerful designs. Birds and insects already operate at MAV like Reynolds numbers. Colmenares and colleagues tested flexible twisting wings and found they improved efficiency by 41% and lift by 35% compared to rigid wings. Flexibility here means that the wing bends and twists during flights, adjusting to the airflow. The adaptation mimics how insect wings or bird feathers move, and it allows much better performance than rigid designs. So, while simulations show us the limits of current MAVs, bio inspired designs show us the possibilities of the future. To conclude, microware vehicles are constrained by three main challenges. They operate at low Reynolds numbers, where aerodynamics behave very differently. They face a higher drag and unusual flow effects like separation bubbles and vortices. They are highly unstable in real world conditions, making control difficult. Researchers have made steady progress with accurate mathematical modeling, optimization of wings and propellers, and numerical simulations. But the biggest breakthroughs appear to come from bio inspired designs. These designs that use flexibility and unsteady aerodynamic effects, just like birds and insects. The future of MAV likely lies in combining these bio inspired wings with advanced control systems and efficient propulsion. This integration could unlock MAVs for real world uses in surveillance, rescue missions, and environmental modeling. So, in short, micro air vehicles are small in size but present big challenges, and nature may hold the key to solving them. Thank you for listening to my presentation. Please let me know if you have any questions.